So welcome to the second part of our exploration of how we can draw graphics within the GAGE framework. As mentioned, this particular one is going to get into a little bit more of the detail in terms of how we're actually going to do things and how we can make use of hardware acceleration given our particular setup. Just by way of context, we finished our first bit having a look at graphics by saying that in GAGE we're going to use a reasonably simple setup. It's going to be a view, full screen view. It's going to be a type of surface view, and we can then overload the do draw method basically to draw bitmaps to this and bring our game to life. So we're going to have a look at how we can do this in terms of a little bit more detail. Now, a large amount of this this part of this exploration is going to be concerned with doing things fast. This is not looking at extreme optimization or fancy algorithms. It's nothing more simple than making sure that when we're drawing, we get our GPU to handle the draw requests, because that's going to be immensely more quick than using the CPU to do things. And that's all fair enough. Now, before we have a look at that, well, actually, let's say we were to delve into our Android documentation to work out what does it take to get things to be hardware accelerated in Android. And again, you can Google this, you can have a look at it on the developers page. You would find there's a nice section actually on hardware acceleration, and you would read a statement saying, okay, beginning in Android 3.0, API 11, which is years ago, so everything is much more compliant than this. The Android 2D rendering pipeline, 2D works for us, that's what we're doing, supports hardware acceleration, meaning that all drawing requests are performed on a view's canvas. So we're using a view and we're going to use the canvas drawing things. That sounds good. We're going to use the GPU. And there's a little bit here about you have to use a bit more RAM because you have generally a bit of video RAM that you're using for doing this. And it says hardware acceleration is enabled typically by default on API level greater than 14, but you can turn it on explicitly if you want to. So if you encountered this page, you would go, job's done. From all versions of Android now basically use the GPU when they're drawing things to a view through its canvas. Okay, that's fair enough, and that's very welcome, and we will actually rely upon that. But I want to talk now a little bit about an aside that will complicate things slightly. And this is good practice, but it does have implications about our ability to draw things being hardware accelerated, but we'll look at this from different points of view. So the side I want to do now is on threading. This is as simple as it gets in terms of threading. We're not going to be looking at complex synchronization or sort of communication between them. This is just simple stuff. And why do we need to think about threading? Well, this ties into a little bit background about how Android apps actually get to be run. So if you're kicking off an app, you don't have any previous instances of it running, it's a new app that starts up. What the Android OS does is that it's going to create a new sort of Linux process for it, give it a space inside which your app can run. And that application gets a single thread of execution. So it's going to be a single thread running your app. And really at that point you can sort of pause, because most mobile devices nowadays are octa-core or other related ones, so they support a wide number of cores. And if you're simply just running things in a single thread of execution, you're not really tapping into the available capacity of your device. Now it says here by default all components of the same application, so if you have different bits, different activities and so on, different fragments, they're all going to run in that same process and hence on that same thread. Unsurprisingly, it's known as the main thread. Okay, so you get that by default. Now let's add a little bit more complexity to this then. So this main thread, the thread that you get, there is only one of them, so unsurprisingly it's going to be responsible for doing a number of things. In particular, it's responsible, it says up here, for dispatching events to the appropriate user interface widgets, including drawing events. So if you interact with the screen, if you touch something, or if there's a request to draw something, Android uses an event-driven model, then you'll have that touch event or that sort of redraw and validate request will be sent off to the particular component so it can process that information. And that sort of dispatching of events that happens on the main thread, that's one of the things the main thread actually does. It's also normally the thread of execution for interaction with the Android UI component. So if you want to interact with, you've got a button up in the screen and you want to change some of the aspects of it, you're normally expected to do it through the main thread. The sort of Android hasn't really written a lot of this in terms of thread safe aspects. So again, if you do it through the main thread, it keeps it nice and safe. So far, so good. Now, where this gets a little bit more complicated then is that if you have an app that needs to do something that's going to take a long period of time. Now, this could be from running a really complex algorithm. Let's say it's a piece of AI that's going to work out some grand strategy, but it takes a bit of time to do that. It could also be loading in or streaming something from a resource over the internet, again, where the process of connecting to and establishing connection may take a bit of time. You should not really, the single-threaded model of execution does not work very well here. Because if you run something on a single thread that takes a long time, then nothing else is running on that thread. And if your main thread, your single thread of execution, is responsible for handling touch inputs and for drawing things in a nice timely manner, then effectively it is blocked from doing that. So if a single thread of control and I go off and do something, then any interaction with the screen, they're not being processed. Any request to draw things or update things, they're not being processed. So basically the application appears to hang, if you like, and the way Android is sort of set up for this, you'll get an ANR, application not responding message appearing if your application hangs for a couple of seconds or doesn't do anything for a couple of seconds or is waiting for your network connection to establish for a couple of seconds. So we need to be really careful about how we use the main thread. So it says here, Android UI toolkit is not thread safe. So if you do want to manipulate or change some of the UI components, it's best to do that through the main thread itself. So you're not going to be changing something whilst an event gets passed in to be handled on it as well. That can lead to unpredictability. Okay, so that's our aside, and that has implications then about how we do things. We can summarize this in a couple of rules. Don't block the UI thread. If you do block it, you're blocking input from the user, and we don't want to do that. If we want to do anything that isn't instantaneous, isn't very, very quick to do, we should be looking to running that in a separate thread, be it a worker thread or a thread that sort of resistant, persistent, keeps around. And if we do want to access or update any of the UI components, it's not really an issue for us under game because we're just going to have a thing called view and we'll be drawing to it. We want to do that on the main thread, the UI thread of control. But 1 and 2 are the things that make a difference for us when we're thinking about creating our game. Now, here we have a model that I'm going to show you some code for that sort of does that. Over on the left-hand side, you can see that we're basically saying that we've got screens and game objects. So these are the things that we have within our game. We'll want to update those so that if it's an AI entity, if we update it, it's going to decide what to do or where to change its position to. We'll also want to draw them, which means we're making them visible on the screen so that the player can see them. In the middle, we've got our 2 arrows. So what we're basically saying here is that one approach, simple approach we're going to use is to have 2 threads of execution. We'll have one, which is our main UI thread. That's the one we get by default. It's already created for us. And for any input, well, that's going to be the responsibility of the UI thread. And if there's any other non-game objects, user interface objects, we'll let that thread draw them as well. But instead, alongside that, we're going to have a second thread that's running our game. And that thread is going to be responsible for updating objects and drawing objects. So this is the most simple approach then to get around this problem. Don't run it in the main UI thread. Fair enough, we'll create another thread and we'll do everything on that thread. Okay, that's our first approach. So let's actually have a look at an implementation of that. You can go through and have a bit of a look at this here. So this comes under our SurfaceView test fragment. So I'm going to show you some code. I'll go through this reasonably quickly because I just want to give you a bit of a feel for what this looks like. Ultimately, we'll be getting onto the GAGE classes so you can see how things are implemented in this. Let me run this one here first of all, and this is going to be similar to what we saw at the end of the first part of this when we were displaying a number of sort of squares on the screen that randomly changed their position. Okay, so if we go down to our SurfaceView test, and I click on this, it's drawing 1,000 rectangles or bitmaps at random positioned on the screen, and it counts up the number of frames that it's drawn. So you can see the thing counting up here to 30, to 35, and so on. So that's all this does. But it's using 2 threads of control. So let's have a look at how this does this here. Now, this is the fragment that we are looking at here. And when we're thinking about this code, one of the things we want to do is to imagine we have 2 threads, 2 separately, concurrently processing activities. And when we're going down through the code, we want to think about, well, here's a piece of code. What thread gets to execute that piece of code? So that's the way we want to visualize and think about this here, because we want to be able to say, this is just one big class here, but this class will be run across 2 separate threads. So as we go through this, we'll try to untangle what gets done in what thread. So first of all, it's a fragment. Now this is an Android UI object, which means that by default when we're creating it and manipulating and making it visible and things like this, it'll be done in the main UI thread. So when we're creating the view, this will be done by the UI thread, it'll be creating it. The view object creates a new SurfaceView render. I'll show you that class in a second. It's just down a little bit here. It's our type of SurfaceView. So this fragment contains one large view, surface view, sized to be the full screen, and that's the surface view that we draw our bitmaps inside. Okay, so far so good. But that piece of code there where we create the view, that's done in the main UI thread and returns it, and this says this is what the fragment looks like. We have a couple of other standard activity and fragment methods here, resume and pause. And the reason we're overloading them here, so whenever you create your application, it's going to be started, made visible, and then resumed whenever it's ready to go. And if we were to go the other way, we will pause it, and then it'll be hidden, and then eventually it'll be stopped when we're making it disappear. When we resume our fragment, and by default that is called as we go through the process of actually displaying it in the first time, we're going to do what we always do. And we're also going to go to our SurfaceView renderer and tell it to resume. Now, why are we doing this here? Let's have a look. So this is the SurfaceView renderer. It's a type of surface view, which means it's displayable, but it also implements runnable. So this actually is going to be a class where the run method will be run on a different thread, not in the UI thread, but on our worker thread. Okay, so that we're just being nice here. We're saying that if we, let's look at pause. If we pause the main UI thread, so we're not going to be pausing our activity for a bit, then we're going to be nice, and we're also going to our worker thread, and we're going to tell it to stop. And conversely, if we go back to resuming our main application or fragment on the UI thread, at that point we'll also start our worker thread. So this is a bit of linkage between the 2 threads. Whenever the UI thread starts or stops or pauses or resumes, we want to do the same with our worker thread. We don't want to have our worker thread keeping on doing things if the UI thread currently is paused. We can just go down and we'll have a brief look then at what resume and pause actually do. So I'm going to skip about the code a little bit, but it's just by way of letting you see how these different aspects happen. So this is inside the actual view object itself. We've got the pause menu and we've got the resume. We'll look at resume first of all. It says if we're resuming, well then we're running our worker thread. We actually create a new thread. So it's at this particular point that initially this will be called in the UI thread, we'll resume it, and we will create a new thread of control, or worker thread, at this point. So whenever we execute line 240, we're actually going to have 2 threads of execution happening. And actually line 241 is when we start the other thing running. And if we pause it, well, we set up a flag saying we're not doing anything. We have a bit here about trying to actually get the thread to join, to basically collapse the 2 things together. We may be interrupted doing that, but we just wait until we collapse the 2 threads together, basically get rid of our worker thread. Okay, so far so good. So what this means, creator activity on resume will be automatically called, and when it is called, we will automatically create our worker thread, and it's going to be doing things. All right. Now, it is complex, but this is the nature of having a little bit of threading included in it. Now, you'll notice then that there's no real other methods up here. And that's what we said. If we go back to the slides, the model we had here was our UI thread's just going to do the things it normally does. It processes inputs, it dispatches those things. But all of the updating and drawing things we will run on our worker thread. So this actually is quite a sort of clear difference between the two. So we create it here, we resume it, we create a worker thread, and that's it. That's kind of the end of the UI thread. Is available for handling touch input and things like that, but doesn't really do anything beyond that. So the rest of the stuff then is happening on our worker thread. So we'll have a look at our worker thread now. There's going to be a bunch of stuff here for here's our image we're drawing out, here's the paint we use for the text, here's the rectangle that we randomly resize, here's a random to help us do that, and here's a long to help us counting up the number of times we've done that. We'll call a setup method. You'll see how this is being executed in a bit. It basically just creates these things. It says let's load in the bitmap, which is just that colorful one. Nothing more than that, closes it down. So setup basically creates these things, gives us the bitmap. That's all it does. We're going to have a do-draw method, and this says here the method that will be called by the render thread when the canvas needs to be redrawn. So our worker thread will be calling this one. We're saying that in this model we update and we draw on our worker thread. So our worker thread is going to be saying I want to draw, and it will be calling this particular method, not the UI thread. The UI thread is just processing input. It'll be our worker thread that is going to be saying actually I want to draw, and it'll be calling this method, and this method will get to be executed on our worker thread. And again, this is the same stuff we've seen before. Randomly create a rectangle, draw the thing out, display the number of times we've done it. We're doing a batch size here of 1,000, so we'll draw 1,000 random rectangles. A bit of overkill, but it just gives you a way of testing the performance on this. Okay, so far so good. Now we're eventually going to get down to the interesting bit for this from a threading perspective. Just before I do that, I'll highlight this line here. We said we had a Boolean flag called running, and it's either set to true, which means our worker thread is running, or false, our worker thread is not running. You'll notice that we're saying it's a volatile variable. Use this here if you have a variable that different threads could change. So it means then there's not sort of caching applied on it, and one thread will not assume that it is false or true because it was recently false or true, but it will always check to see what is the actual value for it. And because we have 2 threads here that can be potentially changing the running value, we make sure we're declaring this to be volatile, so the threads are going to be careful if they're thinking about getting that value. Surface holder, we'll look at that in a second. So here's when we were creating our new surface view. All surface views have a holder, which are the things that sort of look after that surface view. And we'll need to get the holder. If we get it, it gives us our ability to actually write to that surface to display what we want to display, to get a canvas to it. We call our setup, and the setup basically says load in the image and create the paints and basically things like that. Here's the main method, run then. So this is the heart of our worker thread. While we are running, so I'll only do this here whilst the game is currently running. We're not paused, we're not things like that. So while we're running, we make sure we have a valid surface that we can draw to. And again, this is a bit of safety here. If we don't have a surface we can draw to, we're not going to try to draw to it. But when we do have something we can draw to, then that's fair enough, we're going to do that. We go to the holder for this surface and we say we want to lock it. We're going to lock it because we're going to draw to it, and we don't want other things drawing it to it at the same time. When we go to our surface holder and we lock it, it gives us a canvas object that we can use to draw to it. And we're then going to call our doDraw method, and we will pass in our canvas object to that. And the doDraw will then draw the thing out, all of those rectangles to the screen. Finally then, we have done this, and we say we're going to unlock it. So we have finished editing our surface view. If we unlock it, other ones can then edit it. So we're going to unlock it first of all, and post is the second bit of this. Post basically says we've made a change to it. We would like that change to be made visible. So we're then going to post, have it be displayed on the screen. That's it. Now, that sort of holds things together. The key thing to keep in mind here is that this run method and going around this particular thing of locking the canvas, of doing the draw method where we're drawing out this thing 1,000 times at random position, it all gets to be run on the worker thread. Not on the UI thread, on the worker thread. You might be going, why is this relevant? Why have I spent all of this time doing this? Let me show you an example then of it. So, SurfaceView, as mentioned, here it's running, doing 1,000 images, done in the worker thread, and it's displayed as you can see it on the screen. I'm going to do it slightly differently now, except this time I'm going to draw the images, still 1,000 of them. I'm going to use the UI thread. It's much, much faster. So the problem we have that about hardware acceleration, I showed you the web page earlier on from Android 3 onwards is all hardware accelerated. To be more precise, calls and draws that you do on the UI thread are hardware accelerated. Draws that you do on other threads may not be hardware accelerated. And in fact, we'll look at a bit for much later versions of Android where you can make them hardware accelerated. This is a problem for us because if we use a worker thread and we just draw things out naively in that way, we will not get access to hardware acceleration. And there's a massive difference between the speed at which it does it. We want it to be fast, we do not want it to be slow. Okay, so what do we do then as a consequence? So it's slow. If we simply do that naive approach, we will not use the GPU. We'll get the CPU to draw the images out. It's much slower than using the GPU. We need to improve things. Now, thankfully, we can improve things. And to do this here, we need to get the two threads actually working together a little bit. We know that if we draw something on the UI thread, it will avail of hardware acceleration. So that's the thread that we want to draw things on. But if we want to update things, and updating could take a bit of time, we may be loading in bitmaps, we may be doing different things, we want to do the update on our worker thread. So all we're doing is we're separating these two things out. We will update our objects in our worker thread, we will draw them on the UI thread. And at the cost of a little bit of communication between these two threads, we'll get lovely fast hardware acceleration. So here's our new model. Here's something that's a little bit more advanced then. So we still got our two threads of control. We're going to have our main UI thread. We're going to have our sort of game loop, the thing that's updating it. So the game loop will say, I want to update objects. It'll do that first, update all of the objects. And then it will request that I'll send a message to the UI thread to draw objects. So it's going to set a communication to the UI thread to say that I've updated them, can you draw them please? And if we do the draw, it's the exact same code that we're executing, but if we execute it on the UI thread, we'll get hardware acceleration for free. Then we've got a bit of communication. The game loop's going to wait until the UI thread comes back and says, hey, I've drawn all of the objects. At which point our game thread can then say, fair enough, let me see if it's now time to update them again and to repeat that process. Okay, so this is the model. I'll show you the code then that can do this because actually it's going to look very, very similar. So when I was doing the demo, it's the surface view. Here's my canvas thread test. This is the second one. So this is the one that ran much, much faster. Now, I'm actually going to split these things so we can actually see each bit on the screen. Because what I wanted to show you is that the surface view over here, which was the slow one, and canvas view, which is the fast one, they are nearly identical. Nearly identical. So this communication of asking one thing to draw it and then wait until it's finished is actually a small change to the piece of code. So as opposed to having a surface view render, we've got a canvas render, it's just the name we gave to it. We still create things in exactly the same way. Actually, take the space in here so you can see it's exactly the same way. We still resume and we still pause in exactly the same way. There's no difference there. If we go down to how we've declared our class, they both extend surface view, they're both runnable, no difference there. Still declare the same clump of data, still have exactly the same setup method, again no difference, exactly the same draw method. And if you think about it, this should be the case because all we're doing is we're changing the thread that this code gets to be executed on. When it was slow, we were running it on the worker thread. When it's going to be fast, we'll be running on the UI thread because whenever we do draw bitmap here on the UI thread, it'll use hardware acceleration. And if we call draw bitmap over here running on the worker thread, it uses the CPU to draw the bitmap out. That's where the speed difference arises. Most of these things about running and so on is going to be the same. Now we have a small difference over here because we're going to have something, this ties into the communication between the threads, that tells us if we need to draw. Have we finished doing our previous draw and we can then redraw it again, but we'll come on to that in a second. The constructors, again, fairly similar. Don't really have the holder then, things like this here. Running will come back because that is different. For pause and for resume, again, it's the same process. So where do we have a difference? Now it does come into the run method. So that's what we had before. Gets the surface holder, locks the thing, draws it out, unlocks it. What we're doing over here is a bit different. We're still going to keep doing this here while we're running. We're going to check to see, do we need to draw things out? And that's that volatile boolean up here. If it is set to true, it means then that we can draw it out, that we finished drawing out the previous iteration. So if draw is needed, if we can do that, then we're going to set it to false because this is the flag that the two threads use to communicate. The worker thread will set it to be false. And then whenever we have finished doing the draw, which will be in the UI thread, it'll set it back to true. So one thread will set it to false, the worker, one thread will set it to true, the UI thread. And that sort of iteration enables these two threads to work out when they can actually do things. The magic happens here, post invalidate. Now, invalidate is a built-in Android setup. If you invalidate something, you're basically saying that this component has changed. This UI component has changed in some way. It may be a text field where the text has changed. If you invalidate it, it means then that you need to draw the thing again. It has to be redrawn because there's a change in it. And very often you would see Android examples where you're calling invalidate. Post invalidate it's just simply a type of invalidate, but it is designed to be called from other threads. So my worker thread will be executing this loop. It will be going around checking, do I need to draw? If I do, I'm going to post. I'm going to send an invalidate message across to my UI thread. So it sends a message to the UI thread that this particular view, which is the full screen view, it needs to be redrawn. And the UI thread will get access to that and it'll then go, okay, I'm going to draw the thing out. So this is the way that we used to do that. Now what it does down here, this is ugly, but it's just a simple way of doing it. It says, well, I'm going to go to sleep for 10 milliseconds. So it assumes that this is capped at 100 frames per second. Fair enough. So it's crude, it's simple. But this basically says, from the worker's point of view, if I can draw, I'm going to ask the UI thread to draw. I'm then going to go to sleep for 10 milliseconds. I'm going to go back around and I'm going to check to see, is draw needed? Is it being set back to true? If it's set to true, it means that the other thread has finished doing what it needs to do and has changed the flag back. Let's say that the user interface was the UI thread. We were drawing a lot and it was taking longer than 10 milliseconds. So from my worker thread's point of view, it could say, yeah, draw it. It could go to sleep for 10 seconds. It could come around and it could check to see, have you finished? If it's false, it hasn't finished yet, so then it'll go to sleep for another 10 milliseconds and then check again. So it's checking 100 times per second, basically with the UI thread to see, have you finished, have you finished, have you finished? Anytime it has finished, it says, okay, draw the thing again. That's all it does. We've got our on draw down here, which again, just a little way of doing this here. So this is the thing that gets to be triggered automatically within Android. So whilst the run method is run on our worker thread, the on draw method, the overloaded method, gets to be executed on the UI thread. So you'll invalidate it. That'll generate an event. The UI thread will say, okay, I need to draw the thing. It'll go to the view component. It'll say, I'm going to call your onDraw method, and here's a canvas you can use to be drawn to. So you don't need to lock the surface or things like that. It's a little bit more straightforward. But onDraw gets to be called on the UI thread. Okay, so hopefully not too complicated. In terms of code changes, there's not really much change to it, but it does mean then that our main thread will use this in a hardware accelerated manner. Now, there is actually another nice aspect to this, because it's a bit kludgy that if you're not running in the UI thread, you don't have access to hardware acceleration. And again, this is something that's changed over Android's history. So inside Surface, you can actually find this lock hardware canvas if you added an API level 23. So I guess a canvas for drawing the surface after drawing the private canvas, the canvas to post new contents. So, lock hardware canvas, this sounds good. And an API 26, so this is a more recent one. You can actually, this is part of the surface holder. So if we go back to our code over here, so just remember, whenever this is a slow one, in our slow one we had a surface holder which we were then getting, and we're using our surface holder to lock the canvas. But in API 26 we've got a new method coming in. So above this here we should have lock canvas. That's the one we're currently calling. It came in API level 1, ancient, but API level 26 we had lock hardware canvas. Just like lock canvas, but the return canvas is hardware accelerated. Perfect. So in most modern versions then of Android, you can actually, in another thread, lock your canvas and lock it in a way where you say, I want to use hardware acceleration. So let's actually just do that and to see if it makes a difference. So what we want to do there is go into our Gradle file. We'll update the compile to SDK26, the minimum to 26, the target to 26. We'll sync now to rebuild the project. So effectively this is now, you will not be able to run this on an Android version less than API 26. We'll go into a surface test fragment and I should now see lock hardware canvas. So I've changed to lock canvas to lock hardware canvas. I will then run that. And we're using API 27 for the actual deployed device. I don't want to add this thing in. Let's see what we have for our device. So it's installing it. Now, SurfaceView, remember this was the slow one. I click on it this time. Hey, it's fast. So there we are using hardware acceleration. Now, actually, you may notice a subtle difference. So if I were to go to canvas threads, this is the one with the communicating threads. It runs. It is also fast. Now, the thing to note here is the white background. So you can see there's a white background in this one, but if I go back to SurfaceView and run it, there's no white background. And this actually ties into sort of a subtle difference. So if we are using lock hardware canvas, whenever you create the lock to it, you get access to the canvas, but whatever was there before, it's basically it's dirty memory. You need to clear it to a default color, whereas by default, if you were then doing a view, you'd automatically get it cleared to begin with. You get a blank canvas to start with. Lock hardware canvas, you do not get a blank canvas. You need to clear it because you'll have whatever was there in memory beforehand. Okay, so well and good. What we can also say, and again this will come into your decisions, Android also has a distribution dashboard. You can get to see distributions of different APIs, and again this changes over time. So for me recording this today, in terms of API 26, which is the one if you wanted to use a separate thread and to lock it using hardware acceleration, Oreo is the version of Android, the code name. Currently, you've got about 12% of devices that sort of support that style of drawing. Obviously, over time, it'll become up to more or less 100% of devices. But at the minute, if you were doing that, you'd be restricting things down to a reasonably small portion of devices. And for that reason, I'm going to stick with the slightly more kludgy communication between the two threads, because it works really on any version of Android. Right, so far so good. Final thing I want to sort of finish on here before looking at GAGE, and apologies, this is a very long video. If you were doing proper games programming, you would use OpenGL. OpenGL, things like OpenGL or DirectX, these are real meaningful, real powerful standards for drawing graphics. 3D graphics, mostly they're 3D rendering pipelines. You can also use them for 2D graphics as well. They're immensely powerful. They're a bit more complex, and it's simply for the reason of complexity that they're not used in this course. But if you're serious about games development, that's where you want to go to. There you'll get a surface. It will be hardware accelerated, and you get an awful lot of control over how you actually will employ that hardware acceleration. Right, final bit of this then is just to go back and have a look at GAGE. GAGE uses this model of having two threads that communicate together. That's the approach that it uses. I'm going to have a look at the classes now. So I'm just going to call a few of them out here. So inside GAGE now, let me open these up. So we'll go to our GAGE setup. I don't need emulator anymore. So inside GAGE, I will want to have a look at the main game class. And most of it's going to be inside there. This is where we had our timing and things like this here. And we've got a few other ones for interfaces and graphics, basically the view class itself. So these are the bits of GAGE that enable this drawing to happen, enable the timing to happen. So back our slides. So what we're going to have a look at now, our fragment it comes in the game class. It is the thing that's going to be running on the UI thread. The fragment really is going to be concerned with dealing with user interface stuff, nothing much more than that. And also requesting the draw commands. We're going to create our game loop, and it's responsible for updating objects. So the way the game loop is going to work, and you'll see this, is when we're updating objects, we'll go to our screen manager and we'll say, give us the current screen. Is it a main menu? Is it a particular level? And ask that screen to update itself and update all of the objects that it has. When it's finished doing its update, we will then send our request. We'll post and validate, and that'll be a request across to the main UI thread to draw out the UI objects. In this case, we've got one full screen view object, so it's drawing out a single object, the full screen view. And the UI thread, it is also going to go to the screen manager, get the current screen, and it's going to go to the current screen and say, I want you to draw yourself. But we're executing the draw code on the UI thread, hence we're getting hardware acceleration. Whenever we finish drawing out the current screen, it is then going to send a notification across to the game loop to basically say, hey, I finished doing my bit, you can carry on for the next cycle of updating objects. And we will repeat this process. This is how GAGE is going to work and to go around and to do things. Right, so let's have a look at the code, and we'll do this reasonably quickly. So we'll start off with game. So game's the big class. There's a lot to it. If we go down through this here, so in terms of this is for creating. We had a look at this last time for creating the different managers and devices that we have inside it. I'm going to go down to the drawing section. Okay, update and draw. Actually, update and draw. So these are the methods inside our main game thing that's going to be responsible for updating objects and then drawing objects out. So we have our do update, and this is the thing that will be called on the worker thread. And the worker thread is what does it do? Now there's going to be a bit here to do with user input, and we'll look at this when we look at how do we get user input into our game. So I'm going to ignore it here, but in essence at the start of an update we accumulate any input we've received since the last time we did an update. We go to our screen manager, we get the current screen, and as long as we have it we say let's update that screen. So that update is run in the worker thread. And we then notify that that update has been completed. I'll talk about that when we have a look at the game loop, because the game loop structure is a little bit different just in terms of how it deals with notifications. But in essence, when our update is finished, we will update things. The comment there is actually relevant. So assume that if the update is multi-threaded, then the method call will not return until all update processes have completed. And then once this happens, we notify the game loop. So I'll talk about that when I get on to the game loop itself. Notify update completed. The method there, all it does, it goes to the loop and it says that, hey, the update's done. Do draw. So again, this is going to be a method that's going to be called, and we'll look at how this gets to be sequenced in a little bit, because there will be the exchange from one thread to the next. But when draw is called, we'll get the current screen, and we're going to go to the render surface and ask it to draw the current screen. And we'll look at that in a second in terms of how it manages this process. And at some point, not here, at some point we will call notify draw completed, and it'll go back to the loop and say, hey, the draw's completed. Into the game loop itself. So we use sort of a simple Boolean lock class for it to help us manage interactions between it. We have one for update and we have one for draw. We've got our worker thread that is going to be responsible for doing this. Again, we've got a volatile boolean here to tell us if we're running the thing, and the rest of the stuff here is simply to do with timing in terms of updating how long frames should take. We create it. Now, run is where we want to go to. A little bit at the start just to make sure there's a screen we can update. A little bit here about timing, not interested in that. Down here we are. So while we are currently running, what are we going to do? A bit here about timing, let's ignore that. A bit here about working about average frames and things per second, we're going to ignore that. So that's just simply a bit of housekeeping in terms of monitoring time. Here's the relevant bit for an update. So trigger an update. First thing is that we want to basically enable us to say we're going to be updating something now, so we don't want another process to come in to sort of get in the way of doing this. We are going to update, so we're going to lock the update process. We're the only one who wants to be triggering the update. We will then call our do update method, and that's one we've seen above. It'll go to the game screen manager, it'll get the thing, it'll ask it to update itself. And again, we're synchronizing this here, and we're going to check to see, well, has the update finished? And if the update isn't finished, so again, this has almost been designed that you can have a worker thread for the game loop that triggers these things, and you can have other threads responsible for doing other bits of the update. It doesn't assume that the worker thread does all of the update itself. It's a little bit more flexible in terms of who gets to do it. But in essence, we call this trigger update, and then this particular loop is going to wait until the update has finished. And if it's currently ongoing, it will wait until it is notified that it has been finished. Now, the current implementation within this here is single threaded for updates. We don't have a multi-threaded update, so it's a little bit of overkill, but it's flexible enough that if you did have a multi-threaded update, then this will wait until it's told that the update has finished. Trigger a draw request. So similar things here. If we're in the process of doing the draw, well, we want to say yes, we've got a draw going. We'll call our do draw method, and we're going to wait. We're going to check to see then, okay, can I get access to it? And if draw's not finished, then I'm going to wait for it to finish. And that's the interaction with it. Again, a bit at the bottom simply to deal with timing. Right, so let's trace this through if you want to do it this way. So we're on our worker thread. We're doing down through our update. We've finished update, and we're then going to think, right, we want to trigger a draw. So we're going to be calling this method here. Now, this method gets to be called on the worker thread initially. So we'll go to our do draw method. So go to where it's called. So do draw, we're calling this in the worker thread. We're getting the game screen, and we're going to our render surface, and we're asking it to draw it. This is still done in the game, on the worker thread. Okay. Now, if we go here, we see it's actually part of an interface. So GAGE is set up to have sort of a generic render surface, something you can draw to. And for render surface, you can simply draw to it, and you can get it as a view. So for actually creating this, it tried to be flexible, that when you're dealing with drawing, that you're not restricted to one particular model. Rather, it just assumes there is a surface you can draw to, and it's up to that surface to manage the draw in a fast way. Now, we have a concrete implementation of our render surface, which is called canvas render surface. So whilst we are calling the render method, inside the initial implementation of GAGE, it's a canvas render surface is our type of render surface that we do, and we will find the render method here. So this is the thing that gets to be called. So far it's been called on the worker thread. And the worker thread's going to say, right, let me store some information about the amount of time that's elapsed and the thing that has to be drawn. So that's the useful information that we need to hold. And at this point, I'm going to do post invalidate. Okay, so that's the key bit. The worker thread goes down to this level, and for a canvas render surface, it says, right, I know I'm going to be called not in the UI thread, but I'm going to ask the UI thread actually to do the draw. So it post invalidates at that point. And that sends a message off then to our main render thread. So we've got two things happening now. From the worker thread's point of view, it's going to finish render. It's going to, this method here will complete. Do draw will complete. And inside our game loop down here, so we finished our do draw. So worker thread, this has happened. We'll go down here and we'll see, okay, is it currently locked? Yes, it is locked because nobody's unlocked it quite yet. So we're very likely then simply to wait for it to be notified. So that's where our worker thread then pauses and stops at this point, waiting for it to be told the draw has finished. Remember earlier on, we sent the post invalidate through. So that message will be sent across to the UI thread. The UI thread will get it. It will say it's a view object. Okay, I've got to redraw the thing. So I'm going to go to my view object and I'm going to call the onDraw method. So this particular method here, onDraw, it gets to be called on the UI thread. And what do we do here? Well, we set up our canvas for drawing the thing out. We actually go to the screen and we say to the screen, because it's the screen that's responsible for drawing itself, but we're doing this in the UI thread. We say, here's some timing information if you need that. Here is basically a canvas-like object that you can use to draw things out to. And whenever that is finished doing that, so that's whenever the UI thread has finished executing the code that it took to draw the screen to the screen to the screen in that sense, then we will notify the game that we have finished doing that. And if we notify the game, it will notify the game loop, and the game loop will then continue on its process. So it's always a little bit complex just in terms of these things interacting, but that's what happens. Final thing to mention, just in terms of trying to make this generic. So Android has a canvas object, and canvas object has a lot of sort of nice features built into it. For the actual design here, there's sort of a canvas-like entity that was created. So the other interface is one that offers the draw functionality to whatever is drawn itself. So this basically is similar to a cut-down version of a canvas. You can draw some text, you can draw a bitmap, you can draw a rectangle. And in fact, the implementation of a canvas graphics 2D basically is just backing onto a canvas. And then for the particular methods, when you draw a bitmap, it just says to the canvas, draw a bitmap. And if you want to draw some text, go to the canvas and draw some text. So it's just a decoupling between the two. So this tries to set things up that you have as a generic render surface, and you have something that can draw to that render surface. And if you want to use OpenGL or Android canvases or things like this, as long as you create them in a way that map onto this interface, then you can change how you actually deal with the rendering within the program. So the idea is you can have OpenGL, you could have ordinary canvas, you could have an API 26, sort of an ordinary locked accelerated canvas. Different ways of doing it, but it isolates, if you like, from the game engine, the rendering subsystem from the main game loop itself. Okay, this has been horrendously long and complicated, but just to try to tie all of these things together. Android games, in fact Android programs in general, they should be multi-threaded because you've got multiple cores in the device that you're using. Having them multi-threaded is a way of utilizing that. It gives you a lot of flexibility. UI thread, we need to be careful what we run on this. API 23 onwards, any thread can sort of create a hardware accelerated surface. API 26 onwards, if you're using a surface holder, you can also ask for it to be hardware accelerated too, or to lock the canvas in a way that's hardware accelerated. So there are other options inside Android. If you're serious though about games, they're an OpenGL. Lovely. And for GAGE, in terms of the setup that we've used, is worker thread and a UI thread with simple communication between the two of them. We update in the worker thread, we draw on the UI thread, and that's how it does the things that it does. Awful lot to digest and to bring in. Do ponder and go over this here, because it's whilst if you're using GAGE for writing your own stuff, this all happens under the surface. It's useful enough to sort of to know where to understand this, particularly if you want to change how the rendering works to put in a new rendering subsystem. Next video after this, I think we're actually going on to have a look a bit about user input in terms of how we're going to manage that.